Hi there. Welcome back to the wild world of volcanoes, part 5. By now, you should have gone through parts 1, 2, 3, and 4. Are you still with me? Way to go, guys. Well, in part 5, we're going to talk about what comes out of a volcano, the erupted volcanic material. This ranges from solid pyroclastic debris to different types of lava flow. Uh, In Hawaiian lingo, the pahoehoe and the a'a lava, to these very nasty gases that come out of volcanoes. We will also talk about the eruption magnitude and how we rank these volcanic eruptions in terms of the volcanic's explosivity index, or the VEI scale. We will define the different kinds of volcanic cones that we find, from cinder cones to shield volcanoes and the very dangerous stratovolcanoes. And then we will summarize the different types of volcanic hazards, such as your lahars, your pyroclastic flows, the terrible nuée ardente, uh, the lava flows, the ash falls, the gas clouds, etc. So, what actually comes out of a volcano? Volcanoes may eject anything from solid pyroclastic debris, which could be from boulder size to minute uh, ash size particles, to the fluid lava, uh, like your pahoehoe and the A'a lavas, to these very lethal and nasty gases. I will remind you that eruption violence is a function of the viscosity or the thickness of the magma and the trapped gas. Typically, felsic and intermediate magmas are very thick, very viscous, with a lot of trapped gas. So they tend to lead to violent volcanic eruptions. In contrast, mafic magma is much more fluid. They can produce impressive flows of lava that can move at velocities of 25 miles per hour, but they are not the explosive type. On the picture here, you can see the crater of Kilauea volcano in Hawaii prior to the most recent eruptions. After the lava cools, the lava flow may be in the form of a pahoehoe or an a'a type of flow. Uh, Pahoehoe has a smooth, wavy surface resembling that of a twisted rope. In the picture here, I'm standing on a pahoehoe flow near Kilauea volcano in Hawaii. In contrast, the a'a lava is blocky, brittle, rough, and jagged. And here's a close-up of the classic Pahoehoe lava flow with its smooth, wavy, and ropey surface. In contrast, here is a close-up of an A'a lava flow with its very blocky, rough, and jagged surface. Another interesting feature that you may encounter in areas of lava flows are the so-called lava tubes. Lava tubes are natural tunnels in the solidified lava flow. Originally, streams of molten lava flowed through these tunnels. You know, in addition to the solid pyroclastic debris uh, and the lava flows that may come out of volcanoes, you have a whole slew of volcanic gases. Uh, Water vapor, H2O, and carbon dioxide, CO2, uh, combined make about 90% of the gas that comes out of volcanoes. But in addition to those, there's others that are pretty nasty. Sulfur dioxide, SO2, is a very bad smelling gas. If you smell it, you won't forget it. Uh, and then you have your acids and your lethal gases, such as hydrogen fluoride, HF, carbon monoxide, CO, hydrogen chloride, or HCl, that's basically hydrochloric acid, and hydrogen sulfide, H2S, another lethal gas. So how do we rank the strength of a volcanic eruption? Well, we use the Volcanic Explosivity Index, or VEI. Uh, the VEI is based on a scale from 0 to 8. And again, it measures the strength of the volcanic eruption. It operates in a way that is very similar to the earthquake's Richter scale. Each interval in value represents a tenfold increase in the magnitude of the eruption. Mathematically speaking, this is basically a logarithmic function or a logarithmic scale. The vast majority of volcanic eruptions have VEI values that range from 0 to 2. But of course, the ones that we're really interested in and most afraid of are the ones in the 5, 6, 7 range. This table here summarizes the ranking of volcanic eruptions. The more gentle of the volcanic eruptions have VEIs between 0 and 1. And they're basically what we call the Hawaiian or Strombolian type eruptions. The plume height has to do with the height of the cloud of gas and ash that rises from the volcano. In the Hawaiian and Strombolian type eruptions, the plume height is from anything from less than 100 meters to about 1,000 meters in magnitude. And the volume of material that is erupted will range from 1,000 cubic meters to 10,000 cubic meters. From the Hawaiian and Strombolian type eruption, we progress to the Volcanian, even the Volcanian Pelean type eruption. By the time you reach the Pelean category, your VEI now is on the order of 4, and the plume height is now between 10 and 25 kilometers, and the amount of erupted material is now on the order of 100 million cubic meters of material. But the super big eruptions are the Plinian and the ultra Plinian. Now we're talking about VEIs of 5, 6, and 7. An 8 has never been recorded, thank goodness. The plume height now is greater than 25 kilometers, and the volume of material that is erupted from the volcano now ranges anywhere between 1 cubic kilometer to approximated 1,000 cubic kilometers. Volcanic mountains typically have a conical shape, right? So what about the different kinds of volcanic cones? Well, in essence, we have 3 kinds of volcanic cones: cinder cones, shield volcanoes, and stratovolcanoes. Cinder cones develop from the accumulation of solid pyroclastic debris. Therefore, they tend to form steep cones with slopes that can be as steep as 30 degrees, but they're typically less than 500 meters or roughly 1,500 feet high. Shield volcanoes, on the other hand, tend to be very, very large. They erupt mafic magma and form gentle cones with slopes typically less than 2 degrees. The stratovolcanoes are the most dangerous of all of the volcanoes because they're composite volcanoes. They may erupt at different times, anything from pyroclastic debris to lava flows to gas clouds, etc. Generally, they erupt intermediate type magma and tend to be very explosive because of the viscosity, the high viscosity of the magma and the amount of trapped gas. In the picture here, I stand with the cinder cone of Kilauea Iki in the background. This is close to Kilauea volcano in Hawaii. On the left here, you have a picture of another cinder cone. This is one that is found at Sunset Crater near Flagstaff in Arizona. On the right, you have an example of a stratovolcano. This is the infamous Mount Pelée. You can see the silhouette of the volcano behind this building here. So to summarize, the volcanic explosivity index, or the VEI, is based on the volume of ejecta, the material that comes out of the volcano, the height of the cloud, or the plume height, etc. So the scale goes from 0 to 8, with 5 being very large and 7 being devastating is the highest that we have recorded to date. As I mentioned earlier, we have not recorded an 8, thank goodness. Classic volcanic hazards range from mud flows, what we call lahars, that can move at velocities of 30 miles an hour. Lahars are a type of mud flow or debris flow that combines a slurry of pyroclastic debris, rock debris, and water. So they can range from lahars to landslides, landslides that result from the water that is typically associated with the rain that comes with volcanic eruptions, or the melting of the snow cap or the ice cap that you may find on at the top of some of these volcanic cones. Other volcanic hazards include pyroclastic flows. Don't forget about the infamous nuée ardente, this incandescent cloud of gas and ash, and also poison gas that comes out of these volcanoes. Remember Lake Nyos. This material moving at maybe 200 miles an hour. Ash falls and lava flows. Can volcanic eruptions affect the climate? Well, the answer is yes. Most gases blown into the stratosphere disappeared into space. However, sulfur dioxide from volcanic eruptions combines with oxygen and water to create an aerosol of sulfuric acid, H2SO4. The combined ash and the aerosol of sulfuric acid produces a haze that reduces the amount of sunshine that reaches the troposphere and the Earth's surface. The result is climatic cooling. The eruption of Mount Tambora in Indonesia in 1815 led to the year without a summer in 1816. Global temperatures dropped due to a volcanic winter effect, if you will. The gloomy winter temperatures are said to have inspired the author Mary Shelley in the writing of her famous textbook, Frankenstein. Well, guess what? We have completed part 5, so we have one more part to go. The part that will deal with the prediction and the mitigation of volcanic hazards. In the pictures that you see here, it's on the left. I'm in Custer Park in South Dakota, and I'm pointing to the contact between 2 different rock types. On the right, you have the infamous Mount Vesuvius in Italy. So, see you in part 6, where we will talk about the prediction and mitigation of volcanic hazards. See you then.